Okay, so um, there's this concept of microstates. When you study thermodynamics at a higher level or a more in-depth pursuit of thermodynamics is what you're doing, you will have to consider statistics and probability. And that's where microstates come in. So I just want to give you some idea of what that's about. We're not going to do too much with, probability and statistics in this class really, but you should understand how this equation works. So Boltzmann, you probably recognize his name from like the Boltzmann distribution in statistics. And when we study our Boltzmann distributions, we have like the energy of particles, that way, and then the fraction of particles. So for each energy, there's a fraction of particles having that certain amount of energy, and that's described by a Boltzmann distribution. And of course, we can change the temperature and shift this distribution. So that's named after Boltzmann. But this is a different equation, and this is on his grave. The entropy is K times log W. Now back then, when you wrote log, that was assumed to be log base E, which is, now we write ln. And we write now, when we write log, we assume that's log base 10. Okay. We assume log means log base 10. But back then, it meant log base E. So those are the two most common bases for logarithms, and so we distinguish them. ln is natural log based on log base E, and log just means log base 10. But you can, of course, have other log bases. You'd have to indicate what they are. Anyway, this is the equation in a modern form of it. And we have our entropy and our Boltzmann constant, K, and that's our Boltzmann constant. And W is the number of ways, number of microstates by which a distribution can occur. So entropy, the way to think about this in this equation, it's the number of different ways the system can be different at the microscopic level and still have the same macroscopic energy. So let's explore that a little bit. First of all, when you calculate delta S, so you go from your initial to your final state, it's going to be the final minus the initial. You can substitute in this equation now. So K natural log of W for both, but we'll put a subscript F and I for final and initial. Using the rule of logs, we can simplify it. The common term K, and then log of A minus log of A minus log of B is log of A over B. So we just tie those together there. So if the final number of microstates, is greater than the initial, that ratio will be greater than 1, and natural log will be positive. So delta S will be positive. If you go from an initial state to a final that has fewer microstates than the initial, then that ratio will be a fraction, and the natural log of it will be a negative number. So delta S would be negative. So this is a figure that I've pulled from a website. Actually, I made a note of it here, that does a good job of illustrating this concept. What if we had four particles, like four balls or bean bags of different colors, and there were two boxes. And what these pictures represent is if you were to throw all four, and they always land in a box. They never miss the boxes, okay? So they always land in one box or the other. These are all of the different arrangements that you could get. So the arrangement A and E can be different or the same depending on how you describe them. So if you can identify one box versus the other, then A and E are different. So you could say all of the bean bags end up in the left side, or all of them end up on the right side. But if you have a more general description, all of the bean bags end up in one of the two boxes and the other's empty, then A and E are two different outcomes that match that description. And so I've called those the description Roman numeral 1, where you have two boxes, all four bean bags land in one of the two boxes, leaving the other empty, not indicating which specific box is empty and which is full. Now, of course, you could say left or right, or you could combine them into one description. And then my Roman numeral 2 is a description where each of the boxes gets two bean bags. But there are 6 different variations of that description, so that match that description. And so that's the description number Roman numeral 2. And then the description Roman numeral 3, the letter B, the simple description is 3 bean bags land in one box, one on the left, and 1 bean bag lands on the right box. And so you can see there's 4 different possible ways that could happen. And then there's 4 more if you say, well, the 1 bean bag lands on the left side and 3 land on the right. So if you're just describing it without noting one specific box or the other, just 1 bean bag in one box, 3 in the other, that's Roman numeral 3. There's 8 possible variations of that description. So these are all possible outcomes. And how many are there? If you count them up, there are 16 possible outcomes. Now, one thing to note is that each of these is a microstate. The microstate is like any one of these possible outcomes, any one of these possible states at the microscopic level, if we're talking about molecules again instead of bean bags. Each of these, if I throw the bean bags, every single one of these outcomes has an equal probability, 1 in 16, of being the outcome. But when we look at this equation, the microstates are the individual possible outcomes. There's 16 different ones. But W in this equation indicates how many of them match a particular description. So if I take description 1, how many microstates have all 4 balls in one box? Not discriminating left or right, just all 4 balls in one box? Well, there's 2 of them. Okay. So W would equal 2 for that description. Roman numeral 2, that description is how many microstates have balls or beanbags evenly distributed in the boxes? Well, we have 6, so W equals 6 for that description. So my point, oh, and finally, how many microstates have one box with 3 in it and one with 1 in it? Well, there's 8 of those, so W equals 8. So let me go to the next screen to explain this because I have a lot of it written down. Let me explain something here. This microstate and this microstate equal probability. 1 in 16. If I play this as a game, throw 4 beanbags, those 2, any 2, all of these have equal probability of coming up, 1 in 16. But these are microstates, possible outcomes, each one of them a snapshot. But we're trying to relate this to a macroscopic description. So these are macroscopic descriptions. And these W are the number of microstates that match the macroscopic description. Okay. So any microstate has the equal probability, but the condition or the description macroscopic those do not have equal probabilities. So condition 1, the condition where 4 beanbags in one box empty, has a probability of 1/8, 1 out of 8. Whereas the other 2 conditions, 2 and 3, have probabilities of 3 out of 8 and 4 out of 8 respectively. Now you'll notice if you add those up, they add up to 1. All of the probabilities for the different existing descriptions must add up to 1. Okay, so what we see, like if we do this with a sample of gas, you have a sample of gas, you're dividing the volume up, say, of the gas into tiny microscopic cells, 3-dimensional cells. And you're saying that each of those could have a different set of contents, if you will, in terms of energy, number of particles within them, and energy of each particle. So you go from having only 2 boxes in a 2-dimensional picture to an extremely large number of boxes with a 3-dimensional aspect to it. And we are trying to we are trying to come up, when we do this at a higher level of statistics, we're trying to come up with a statistical picture of the different ways that the particles and the energies could be arranged in that big three-dimensional lattice of fictional cubes. In each one of those possible pictures has equal probability, but the macroscopic description of of how the sample is, there are different probabilities for each description. Okay, so we can relate you can see that this has sorry, yes, here I'm getting ahead of myself here. We could calculate the entropy. We can also calculate the change in entropy for any one of these macroscopic descriptions. So, for instance, if the final state has all in one box, that's condition 1, W equals 2, and S would be K natural log of 2. If the initial state is condition 3, where W is 6, there, oh, did I do this wrong? You know, let's, I messed that up. Let's say, because I've already done the math, let's say this is condition 2. So instead of evenly distributed, oh no, that is right. I'm sorry. Yes, condition 2, evenly distributed. I apologize. So W is 6. So S would equal K natural log of 6. Now, we could calculate the entropy of each of those states like that. Plug in, take the natural log of 2 or natural log of 6 and multiply Boltzmann's constant. Or if we want to calculate delta S, we could use this equation. So let's do that. So we have the final, W is 2 over the initial, W is 6. That's 1/3, natural log of 1/3. And you can see the initial state has higher entropy than the final state. W is greater for the initial state. So we are going from, this state 1 is very concentrated energy, if you will, energy of the particles. So it's going to be low entropy. This is more dispersed. So it's going to be high entropy. And you can see why some people just summarize and say orderly and disorderly. So condition 1 is more orderly. Condition 2 is more disorderly. But it also has to do with the number of possible ways you can reach that description. Condition 2 has 6 possible ways to reach that description. So in that sense, it's more disorderly because it can be achieved many different ways. Condition 1 is more orderly. There are fewer ways you can achieve that condition. So if you take this to a macroscopic example, entropy is about relating what's going on in a microscopic scale to a condition at the macroscopic scale. But let's put that aside for a minute. If you take a room, for instance, let's say a bedroom, you could have disorder, and the disorder, you might describe it a certain way, but there's many different kinds of conditions. So maybe the bed isn't made, and there are many different ways the bed could appear that it's not made. The position of the sheets and the blankets and stuff, and clothes on the floor, equal kind of description, but the clothes could be in one corner or the other. So being disorderly gives many possible ways of having that condition of disorderly. But when you clean the room, the bed is made perfectly, everything's put away. There's only really one state that describes that condition of being a made bed, cleaned up room. There aren't multiple possible ways to achieve that description. So that by its nature, a more disorderly description can occur in many, many different ways. Okay, so we are going from a more disordered state to a more ordered state, and notice that we get a negative, because entropy, if it goes down, the system's becoming more orderly, more concentrated in energy. Now, K, the Boltzmann constant, is a very small value, and our values for W here are really small. Also, well, that wants something to do with the final number we get here, but those numbers are small. Normally, we'd have many more. We'd have a bigger, instead of just two boxes, you have a large volume with many, many, many boxes that require statistics to actually do this. But anyway, this is a very small number, but that's when you're talking at this Boltzmann constant, this 1.38 times 10 to the minus 23rd is not a per mole number. It's it's the molecular level, if you will. So you'll notice it's 10 to the minus 23rd if you have a mole. If you have a mole of particles and you multiply that, you'll get a much larger number than you see there. But anyway, this is how we can get our entropy change, delta S, by considering the number of microstates that fit the description of the initial state and the final state. Now, I just make a comment here without doing it. Here we had two boxes, 6 particles. I'm sorry, 4 particles. If you were to increase it to 6 particles, you would find that the probability of having all 6 on one side or the other, I drew them on the left, but one side or the other, the probability is 1 in 32. So the conclusion is, if we just take that simple description, which is the least likely description, is that all of the particles would concentrate on one side, that probability of all particles being in one of 2 boxes decreases with the number of particles. So if you only have 4 particles, you have a what was it, a 1 in 1 in 8. Yes, 1 in 8 probability. When you go to 6 particles, it drops to 1 in 32. So you can imagine this picture here. I mean, look at all the particles we got. Having those particles just somehow all end up on one side. We're not talking about 4 or 6 particles. We're talking like a mole of particles. The odds of that happening are very, very small, almost approaches zero compared to the odds of the particles just being evenly spread through the two containers. So if we were to do the spontaneous process, open up the stopcock and let the gas have the opportunity to go to the other side, we would expect it to be, that would be spontaneous, because W here is much greater. So delta S, we're letting energy become more diffuse, and delta S would be very positive. If we go to the non-spontaneous, of course, the W is much greater on the initial condition, and we would have a negative delta S, and the probability would be almost zero, as I said.